Hello there. This video is on section 4.2, talking about the mean value theorem and Rolle's theorem. And I'm going to be showing you what they are, how to use them, and when they are valid. Just as a short intro, this is kind of an example of where the needs of professional mathematicians differ a little bit from the needs of students of calculus. From a professional mathematician's point of view, these types of theorems, the mean value theorem, Rolle's theorem, they are really integral to a lot of the reasons why, critical points, inflection points, all these kinds of things that we're doing work. From a student perspective, these are just kind of strange little things, strange little facts that we use to discover something which doesn't seem to be that important. So just kind of keep that in mind that these are fundamental building blocks from a mathematician's point of view, and therefore they want you to experience those fundamental building blocks. Perhaps from your perspective, there is not a lot going on. You're maybe looking for some hidden meanings, maybe trying to figure out how it can be more complicated. Hopefully, by the end of this video, you'll realize it's not more complicated. There are just a few steps to do for each of these to be able to use them and verify them. And that's sort of what our mission is today. Okay, so let me first of all explain what these two theorems are, the mean value theorem and Rolle's theorem. So the mean value theorem, and I had them written right here on the screen, mean value theorem, it's only valid for functions that are continuous on some interval. So we say that f of x is continuous on some interval from a to b. It also has to be differentiable from a to b. Technically, it doesn't even need to be differentiable at the endpoints, but that's just kind of splitting hairs. So it's a continuous and differentiable interval. We also have the idea that we can find slope. Slope is y2 minus y1 over x2 minus x1. And that's, just reminding you that that's our slope formula. So what does the mean value theorem say? Well, if you have this continuous and differentiable function, then we know that there's some number, this is an x number, by the way, there's some x equaling c where the derivative evaluated at that c is exactly equal to the slope through the endpoints. This is the slope with y2 minus y1 being at the extreme, beginning and ending of the interval. So finding the slope through the start and end of a function, you can always find a point where the slope is also the same. So let me illustrate an example here. You have some kind of function. You have a starting point, you have an ending point, and from the starting point and the ending point, you can find a slope. Usually we represent that as like a line because slopes are how much a line increases or decreases. So we have a slope of this line, which is, this is our B, this is our A. So it's just, y2 minus y1 over x2 minus x1. And all the mean value theorem is trying to say is that somewhere along this place, there's some value of C. Let's say here would be the value of C, where the tangent line slope is exactly parallel or the same as the slope to the endpoints, right? And that's just guaranteed that we have some place. It can happen more than once. Like I think maybe over here is another place where we would have another possible value. See, there's not just one value of C, but C has to be somewhere in the interval. We guarantee we can find a derivative, a tangent line slope, which is exactly equal to the slope to the endpoints. So that's what the mean value theorem is saying. All right, let me tell you what Rolle's theorem says. So Rolle's theorem, again, it's only valid for a continuous and differentiable function. So again, it has to be continuous on some interval and differentiable on interval, not necessarily the endpoints, but who cares? And so what does the Rolle's theorem say? Well, first of all, you have to have the y value at each endpoint being the same. So instead of my example up here with the mean value theorem, where I can start down here and work my way up here, the example for Rolle's theorem, or where Rolle's theorem works, is that wherever it starts, it has to return to that place. So this value here has got to be the same for both endpoints. So this is my f of a and f of b being at the same place. So that's what this says right here. F of a has to equal f of b. So the endpoints have the same y height. All right. So if we have that situation, what do we know? So once we have that information, again, we know something about the derivative. We know there's a place where the derivative is equal to 0, right? And that's sort of the same thing as the mean value theorem. We can get to these 2 points right here. They have a slope of 0, right? So it's kind of a corollary to the mean value theorem, right? So there's some location, maybe more than one. We'll call it C, maybe right here, for example, where the slope here is equal to 0. And there could be more than one. I guess this is not technically a function because it kind of goes back on itself. So let me draw this so it actually looks like a function. I'll pretend I can go down there too. Okay, so it's got to have only one y value. Okay, so that's Rolle's theorem. Let's just see a couple of examples of what they would want you to do with these to become more familiar with mean value theorem and for Rolle's theorem. Okay, so I have an example here of Rolle's theorem. So my example A here, leave this a little bit visible. So for example A, we're supposed to verify we can use Rolle's theorem for this particular function on the interval from 0 to 1. And then we're supposed to find the value of C that satisfies the Rolle's theorem. Of course, that value of C has to be in the interval from 0 to 1. All right, so what are the ways we verify? Well, we need to verify that it's a continuous and differentiable function. So is this continuous? So we'd have to say fx equals this function they gave us. We'd have to say it's continuous. And why is it continuous? Well, it's made up of 3 continuous parts. It's the sum of continuous functions, right? So if you have a continuous function, you add it to the continuous function, it's still continuous. There's no division by 0. There's no logs of a negative number, etc. Right? So we know it's continuous because it doesn't have any undefined places. Okay. There's no place where we can possibly find a value of x where the limit from the left, limit from the right, and the value of the function don't all agree, right? Because each of these parts are continuous themselves. So that's first thing we need to verify. I'll put a green check mark next to that so we know it's continuous. We need to say that f of x is differentiable. Well, can we find the derivative? So the derivative, which is df dx, we can apply our rules for differentiation. So the derivative certainly exists. Is it differentiable on the interval from 0 to 1? Now you have to be careful here. I set this up so that, it wouldn't be trivial. It turns out this is a problem here because we have a division by 0. df dx is 1 over 3, and this is a negative exponent, so it's 1 over x to the 2/3 minus 1. Yeah, that's a 3. So this is not continuous. It has a problem, so it's not continuous at x equals 0 because you can't divide by 0. It's continuous everywhere else. There's no other problems. So that's the only place, right? So it is continuous. Everywhere else. And I don't know why I'm writing sideways, but it's okay. But specifically, what do we need to know that the derivative is continuous? So we'll say the derivative, just to emphasize, the derivative is continuous everywhere else. The derivative is not continuous on 0. So derivative is not continuous on 0. But remember that we only need a continuous on the interval from 0 to 1, and it doesn't even need to be including the endpoints. It just needs to be differentiable between a and b. We didn't even care about the endpoints. So is this function differentiable between 0 and 1, and we didn't even care about 0 and 1. And the answer is yes, it's continuous everywhere else. So we can do continuous from 0 to 1. So we get is continuous. Derivative is continuous. Because it's different, it's continuous. The derivative is continuous everywhere except for 0. So certainly it's continuous from 0 to 1 or 0 to 7. We only need 0 to 1 because that's our interval. So you have to verify that it's continuous. You have to verify it's differentiable. And sometimes you need to make a little argument because it may not be differentiable, but the location is not differentiable, may not be relevant. And the last thing we need to verify is that it's the same in each endpoint. So the function at endpoint A is equal to the function at endpoint B. So we have to verify that f of A question mark f of B. Right? We'd have to verify that because that's part of Rolle's theorem. We have to verify the endpoints have the same y height. All right, our endpoints are 0 and 1. So what we're trying to verify is that f of 0 is equal to f of 1. And we can just take the function and plug in 0 and 1. So if I plug in 0, I get 0 to the 1/3 minus 0 plus 2. And over here, I plug in 1, I get 1 to the 1/3 minus 1 plus 2. All right, so just doing a little math here. 0 to the 1/3 is 0. 0 minus 0 is 0, so we get 2 here. And this is 1 minus 1 plus 2. And that's the same. 2 is equal to 2. So that's verified as well. So we're supposed to verify that we can use Rolle's theorem. We verified the function is continuous. We verified the derivative is continuous. We verified that the f of A and f of B are the same. All right, so now we're allowed to use Rolle's theorem. So what does Rolle's theorem say that we do with it? Right? What is the using it? We're going to find a number c where the derivative at c is equal to 0. Well, we know what the derivative is. We just found it. It's over here. This is the derivative. So we know there's a value of c where we could plug it in and find that it's equal to 0. So the derivative, evaluate c, I'll write f prime of c. That's this thing with a c plugged in. You can do it with an x, it doesn't really matter, but I'm going to do it like the book does it. Put a c in there, and then you make it equal to 0. So we know that we can find a solution to this equation. We're guaranteed that there's some value of c, and not only that, c has to be between 0 and 1. All right, so let's do some algebra here and just solve for c. Just moving things over, adding 1, multiplying by 3. And then I'm going to raise everything to the negative, the negative 3/2 power. So I'll take this thing, raise it to the negative 3/2 on both sides, of course. And then what we have here on the left-hand side is we have two exponents. We have the c to the negative 2/3 and c to the negative 3/2. So if I multiply those out, those exponents, I get c to the 1. Oh, that's not 1. I was trying to fix it and I fixed it wrong. If I multiply both sides by 3 up here, then I end up with a 3 in there. Okay. There we go. So you get 3 to the negative 3/2 power. And that's my value of c. Let's verify that this is actually between 0 and 1 by plugging this into some computing device. Okay, so just let me get rid of this old stuff here. So 3 raised to the negative 3/2 power is approximately 0.192. Which is between 0 and 1. So we found the value of c that satisfies Rolle's theorem. It's 3 to the negative 3/2 power, and that's it. That's it for what you need to know about Rolle's theorem. It just has some conditions you need to verify. Essentially, three of them. Is the function continuous? Is the function differentiable on the interval, of course? And then you need to find the derivative, set it equal to 0, and then you get your essentially you get your critical point, right? You take the derivative, set it equal to 0, but we don't call it this point. We're just saying we're guaranteed that we can find a value of x called c, where you get the derivative equaling 0. That's it. Nothing more to read into the situation. All right. So let's move on to an example with the mean value theorem. Let me zoom in a little bit. I'll just remind you because it's on a new page. This is what the mean value theorem says. Again, you have to have a continuous and differentiable function on an interval. And then what we're going to do is we're going to find the slope through the endpoints. That's this guy right up here, slope to the endpoints. And we know that we're going to be able to find some value, c, somewhere in that interval, where the derivative at that value is the same as the slope. Remember, when they're doing c's here, c is an x value, right? So it's x equals c. Some people get confused with that. They're just calling it c because they're trying to be more complicated, right? It's just some x value between a and b. All right, so we have our function again that we had before. We're going to verify the mean value theorem. The first two parts of the mean value theorem are the same as for Rolle's theorem, where we have to say that the function is continuous. And we'd have to say that the derivative is continuous. And we actually don't need it continuous everywhere. We only need it continuous on the interval from, well, in this case, 1 to 8. The interval that was given to us was 1 to 8. So this is continuous on the interval from 1 to 8. And the derivative needs to be continuous on the interval from 1 to 8, but technically we don't even need the endpoints like this. Well, we did this kind of argument before. This thing is the sum of three continuous functions. So it's the sum of three continuous functions. And so the sum of continuous functions is still continuous. So it is continuous. All right, what about the derivative being continuous? Well, let me remind you what the derivative is. We need it again for this problem. So the derivative is the 1/3 x to the negative 2/3 minus 1, same problem we did before. I can write this in fraction form, 1/3 times 1 over x to the 2/3 minus 1. Its only point of discontinuity is at 0. So the only point where it's not continuous, again, I'm doing sideways writing today, is x equaling 0. So if that's the only place where it's not continuous, so we know, so this derivative is continuous everywhere else, specifically from 1 to 8. I guess we don't need the less than or equal to sign, but again, it doesn't matter very much. So we know that the only place is not continuous is 0, but that doesn't matter because our integral does not include 0. Notice if this said negative 8 to 8, maybe, on another problem you see negative 8 to 8, we would say this fails the conditions for the mean value theorem. So we're not allowed to use the mean value theorem unless it is, in fact, continuous and differentiable in the interval. So if they wrote negative 8 to 8, you would say, oh, can't do it. I'm done with the problem, right? So at that point, you just say, I'm done because it doesn't, it's not valid. It doesn't match the conditions for the mean value theorem. Okay. It doesn't say negative 8 to 8, so we don't have to worry about that. So we verified the continuous and differentiable, and there's nothing else to verify. I am going to calculate the value of m because we're going to need to know it. But that's it we need to verify for the conditions of the mean value theorem. So the value of m is the value, it's the slope, slope of the endpoints. It's just y2 minus y1 over x2 minus x1, where you use the endpoints. So this is f of 8 minus f of 1 over 8 minus 1. All right, so I'm going to compute f of 8. So over here, I'll just do here. F of 8 is when I plug in 8 to this thing. 8 to the 1/3 minus 8 plus 2. That's the y2. And then I subtract off y1, which is when I plug in 1. 1 to the 1/3 minus 1 plus 2. And then 8 minus 1 is 7, so I can do bottom. All right, let's see if I can do this and not use much more space. 8 to the 1/3 is 2. So this is a 2 minus 8. So this is 2 minus 8 plus 2, which I believe is -4. So we get -4. Here we get 1 minus 1 plus 2. So we get -4 minus 2 over 7, which is, I'm going to squeeze this in over here. -4 minus 2 is -6 over 7. All right, let me double check that I did this. 8 to the 1/3 is 2. 2 minus 8 is -6. -6 plus 2 is -4. Yep. 1 to the 1/3 is 1. 1 minus 1 is 0. Plus 2 is 2. So it's this creature, -4, minus that creature, -2, which is -6 over 7. All right. So now we're going to find a number c. This is an x number, of course, where the derivative at c is equal to the slope, -6 over 7. So we know the slope equation. So I'm going to write that down and set it equal to -6 over 7. Okay, so you just have to do the algebra now and solve for x. I forgot to put in the c. As I mentioned before, some people just solve it for x. You're officially supposed to put in a c. So you're supposed to find f prime at c. So let me just fix that by writing this as a c instead of an x. It's the same darn equation, right? It's no difference. So write it as an x if you want. It's fine. Just write it as c at the end. At the end, just pretend that you were doing a c all along. All right, so I'm going to add 1 to both sides and just do the normal like algebra solving thing. So c to the -2/3 times 1/3 has to equal, if I add 1 to both sides, I'm adding 1 to -6/7, which is positive 1/7. -6/7 plus 7/7 is positive 1/7. So this is 1/7. I'm going to multiply both sides by 3. I'm running out of room. So I'll just put a little arrow here. That gives me c to the -2/3 is equal to 3 over 7. And then I'm going to go a little bit to the right again. I'm going to raise both sides to the reciprocal exponent. So, raise it to the -3/2 power. So I get c by itself. So that gives me on the left hand c to the first power, which is just c. On the right hand side, I get 3 over 7 to the -3/2 power. -3/2 power on both sides. So that's my value of c that is supposed to, be the one that I'm looking for using the mean value theorem. Now, this value of c is supposed to be between 1 and 8. So let's verify that it's between 1 and 8, because if it's not, we did something wrong. So 3/7 to the -3/2 power. So 3 over 7. Oops, I'm doing it in the wrong place. 3 over 7. I'll use parentheses. Sorry, I'm being slow today. 3 over 7 raised to the -3/2 power. I probably don't need all those parentheses, but I'm worried that I'm going to do something wrong. All right, so 3 over 7 raised to the -3/2 power is about 3.564. So this is c is 3.564 approximately. Is that with our interval? Yes, it is. Our interval is 1 to 8. So we know that C is between 1 and 8. I'll just write C here since we know the value of C. And that's what we're supposed to do. That's it. You're supposed to verify that the function is continuous and differentiable. And then you're just supposed to find the derivative equal to the slope through the endpoints. And there's going to be a value of C somewhere in the interval, which is going to be exactly equal to that slope of y2 minus y1 over x2 minus x1. All right, so I have one more example here of the mean value theorem. I will invite you to try it before you see my solution. It's example C right here, where we have a function equal to the square root of 2x plus 1. We're supposed to verify the mean value theorem on the interval 0 to 4. And then assuming that it verifies, you're supposed to find the value of C in the mean value theorem that actually works according to that theorem, where the derivative at C is equal to the slope to the endpoints. So if you have a little energy, give it a try, see if you can go through the steps, and then come back and I will show you my solution and go through the steps of how I got my answer. So I'm going to pause, write out my solution. Hopefully you pause and try your solution. We'll come back and we'll match up to see, how much our solutions look similar. All right, so I've written out my solution and I'll go through the steps with you. Hopefully you had a chance to try it yourself. So first I need to verify that the function is continuous on the interval. This is a square root function. We are not allowed to take square roots of negative numbers, at least the answers are not real. And so we cannot have the square root of a negative number. So this is not continuous for everything. It's continuous only if we avoid taking a square root of a negative number. So the inside part, 2x plus 1, has to be greater than 0. So I wrote down the condition that makes this continuous. The inside can't be negative, it has to be greater than 0. And I solve for x. So I know it's continuous whenever x is at least as big as negative 1/2. Our interval is from 0 to 4. So since it's always continuous when x is bigger than or equal to negative 1/2, it's definitely continuous on 0 to 4, since both those numbers are larger than negative 1/2. And I have checked the first part of the mean value theorem. Second part of the mean value theorem says that the derivative needs to be continuous on that interval, not necessarily at the endpoints of that interval. So first I computed the derivative using the chain rule, and I simplified a little bit. It is a fraction. It also has a square root. 1/2 is a square root. So we have two things to avoid. We can't have division by 0. That's not continuous, not computable. And we can't have a square root of negative number as before. So this bottom part, the 2x plus 1, that can't be 0, and it can't be a negative. So I just wrote that as the bottom part has to be not 0 and has to be greater than 0, right? It has to be positive and not 0. So I end up with a very similar kind of equation saying that this derivative will be continuous as long as x is bigger than negative 1/2. And our interval 0 to 4 doesn't have anything to do with negative 1/2. Both numbers are bigger than negative 1/2. So we have verified that the derivative is continuous on the interval from 0 to 4. All right, so the only other step we need to do is just find that value of C that the mean value theorem guarantees that we can find. So I found the slope to the endpoints, y2 minus y1 over x2 minus x1. I got a slope of 1/2. So that's my m value right there. And then I found the derivative from before. I just wrote it down with a C in there instead. And I set it equal to 1/2. So I took the derivative equation and I set it equal to the slope value. The slope value, remember, was 1/2. So I made those equal to each other, did some multiplication to simplify this, squared both sides, and solved for C. And I got C is equal to 3 over 2. We do need to verify or just double check that C is in fact in our interval. So our interval from 0 to 4, 3 over 2 is definitely 1.5, right? And 1.5 is between 0 and 4. So that is indeed the value of C we're looking for that satisfies the mean value theorem. All right, well, that's it for today's lecture. Hopefully this was helpful for you in doing the homework in 4.2. And please reach out if you have any questions or want any help with anything that you're working on. I hope you have an enjoyable day.